we present Neural-PIL, Neural Pre-Integrated Lighting for Reflectance Decomposition. Given a set of object images captured under different illumination conditions, as shown on the left side, our goal is to reconstruct the object shape while also decomposing its material properties such as diffuse albedo, specular albedo, roughness and normals. In addition, we also estimate per-image illumination. This enables novel view synthesis and relighting of objects in new environments. For this, we construct a neural reflectance volume where at each 3D location, a density and BRDF is estimated as illustrated in this figure. The main challenges are that rendering with passive illumination and BRDFs is expensive, and the solution space is complex for this highly ill-posed problem. Some very recent works aim to tackle this challenging problem, namely NERD, Phi-SG and NeRF. NeRF requires known illumination but handles interreflections. NERD and Phi-SG estimate illumination, appearance and shape but leverage spherical Gaussians to model the illumination. Whereas, we propose a more efficient neural illumination representation. As shown in the generic rendering equation here, integrating light over the hemisphere is central for rendering and the most expensive operation. For offline rendering, this is more or less done by calculating this integral numerically. However, even in numerical integration, a larger number of samples are required and artifacts from the numerical integration are usually present. A standard technique is to use spherical Gaussians to represent illumination, thereby converting the light integration into convolution between spherical Gaussian and analytical BRDF model. On the left, we visualize fitting spherical Gaussians to an environment map with an increasing number of lobes and then using the resulting spherical Gaussians for rendering. The rendering time increases drastically with increasing the number of spherical Gaussian lobes while we can still observe several discretization artifacts. To address this rendering issue, we take inspiration from a technique called pre-integrated lighting that is often used in real-time rendering. The key here is to convert expensive integrals in the rendering equation into simple additions and multiplications with pre-integrating parts of the illumination. For a better illustration, we visualize this light pre-integration technique in 2D. Let's take this example environment map and see how the light pre-integration works for this. The pre-integrated light depends only on the incoming illumination direction ωr. In addition, this light integration depends on the surface roughness. A rougher surface equals a wider distribution of reflected rays towards the environment map, resulting in a blurrier representation on the object. In real-time rendering, this light pre-integration is brute force computed in an offline manner for all the incoming light directions and roughness levels. Once computed, this enables fast rendering. But this light pre-integration is still expensive, and doing this on the fly in our training loop with estimated illuminations is not feasible. We thus propose a technique which replaces the offline, brute force light pre-integration with a neural network. Given an embedding which describes the illumination, we first sample the incoming light direction. We propose a network that is conditioned on illumination embedding. This network architecture is inspired from Python with film siren layers. Then we add an additional conditioning network that is conditioned on the surface roughness. The resulting output acts as a proxy for pre-integrated light. We call this network Neural-PIL, and this converts the complex light pre-integration process into a simple network query, making the rendering quite fast and effective. Compared to using spherical Gaussians, rendering with Neural-PIL is several orders of magnitude faster. At the same time, using Neural-PIL can produce more accurate reflections with fewer parameters compared to using spherical Gaussians for rendering. Another key technical contribution of this work is the learning of deep priors with smooth manifold auto-encoders. We find that using simple auto-encoders is not sufficient to learn smooth low-dimensional manifolds to represent BRDF and lighting. Thus we propose to enforce this smooth manifold by explicitly interpolating between embeddings during training, and defining a set of losses which ensure smoothness between the endpoints. This figure shows the interpolation of BRDFs with and without using smooth manifold auto-encoders. Here we apply a specific BRDF to each corner and interpolate the latent space in between. Notice the smoothness of interpolated BRDFs when using SMAEs compared to without using SMAE. We now show several results. Here we show sample novel view synthesis and relighting results with different illuminations. Also shown are the sample input images to our technique that are taken under different illumination conditions. Here we show comparison of novel view synthesis results of our technique with NeRF and NeRD. NeRF produces floating artifacts whereas NeRD does not capture fine details. In contrast, our results capture more details with less artifacts. Quantitative results on synthetic datasets demonstrate superior BRDF and light estimation using our technique compared to existing related techniques that also perform BRDF decomposition under unknown illumination. View synthesis results on the left, and joint view synthesis and relighting results on the right also demonstrate better PSNR and SSIM scores compared to existing related works. In summary, we propose a technique that estimates shape, BRDF and illumination from images taken under different lightings. We address two key challenges in this work. We propose Neural-PIL technique for fast and effective rendering. We also propose smooth manifold auto-encoders to learn smooth low-dimensional embeddings to represent both BRDF and lighting. Experiments on both real-world and synthetic images demonstrate state-of-the-art decomposition, view synthesis and relighting results. Thank you for watching. Code will be released upon publication and see the paper for more details.